next step, you start asking, all right, what do I know? What I'm looking for? You know this, and you're looking for this. That's also, again, a straightforward application of a general strategy. A general strategy always starts from a statement of the law you want to use, as generic as possible, statement of a definition or definitions you want to use, and then application those general statements to a specific situation, and then wherever equations tell you, you do it. Just follow the lead. Yes?
So in that situation, I mean, you get mu tension is equal to mg, right? If you put it on the other side.
I'm going to solve the whole problem.
Okay. Well, so my question is if the force of tension nu is equal to the force of gravity, how is it moving?
Well, if I trust this gentleman, it says, the problem says, it's traveling at constant velocity. If velocity is constant, it doesn't really matter if it moves up or down, as long as velocity is constant. And we know that the acceleration has to be equal to 0. So the question, how does it moving in this situation, just doesn't matter, as long as velocity remains constant. If velocity starts changing, the direction will matter. All right, so one more reminder, especially about the time. The class starts at 8:30, but the exam starts at 8. So everybody who arrives at 8:30 will have 30 minutes less, because at 10, the next class starts. The exam ends at 9:50, like the class. So, all right. And hopefully we're going to have more time today for questions and answers. So this is kind of already a review, in a way. So Atwood's machine, this is this device. There is a pulley, frictionless, and in this situation, ideal, massless. And we have two weights attached to an unstretchable, massless string. And too high, even for me. You put it across the pulley. In a lab, or yesterday, we've solved the problem when we had two objects connected by a string. But in that situation, one object was traveling horizontally and second vertically. So now we just have physically same situation, but they both travel vertically. This is 100-gram weight. This is another 100-gram weight so far. So what do you think will happen if I let them go, just release them? You said, and you said, so what do you think?
Did you say they're both?
Yes.
Then they should just stay.
Exactly. There's no reason to win. So we need to have one heavier or lighter. And to do that, I can just add an extra mass. It doesn't matter higher or lower, because this level doesn't matter. What matters is which is heavier, which has more mass. So I can even start from this level. Now, this has a little bit more mass now. So what do you expect will happen if I let it go? The heavy starts traveling down, the light starts traveling up. Yep. It doesn't matter if this initially is higher or lower. Yeah. So the level doesn't matter. What matters is we actually can measure. Well, we can measure height. We can measure time. And we can calculate acceleration. Yeah. Time, distance, initial velocity is 0. And we can calculate acceleration. Well, they have opposite accelerations, but the magnitude of the acceleration will be the same for both because of what? What is the reason? The fact that the string is massless tells us that tension is the same. Massless string means the force of tension in the string has the same magnitude everywhere. What is the reason for these objects? Yes?
I was going to ask what would happen if
Take 211. So, what is the reason for these objects to have exactly acceleration with exactly the same magnitude? What do you think? Yeah? No, you know, it's in your memory. You just need to dig in. Yes? No, it's not going to be gravity. You see, how do we make the acceleration to be gravity? You take scissors and you cut the string. And in that case, the string doesn't touch anymore. It just falls. That when acceleration is equal to gravity. When the string is attached to it, it messes it up. The acceleration is not equal to acceleration to gravity anymore. It just can't. But the question is, the acceleration of this guy has the same magnitude as the acceleration of this guy. Why? Yes. Yes. You already, yeah, let.
Their displacement is the same, so their velocity is the same.
Why?
Because they're traveling the same distance.
Why?
Same amount of time.
Why?
Because they're attached by a string.
Why? What's so special about this string?
That's a big size.
It has a fixed, well, length, we should say. It's unstretchable. Normally, there's always a final reason in physics. That reason either goes from the property of an object, and this property is unstretchable. You can replace this string with a rubber cord, and everything changes, because the rubber cord is stretchable, and these motions will not be coupled anymore. So they will travel different distances in different times, velocity will be different, acceleration will be different. You want to solve that problem? Take PY 351. That's it. So, but what I'm saying is, this experiment actually has been done more than 200 years ago to measure, first time very accurately, gravitational acceleration. Because this acceleration is not g, but is directly related to g. And all we have to do is just apply the Newton's law. How many times do we need to write the Newton's law for this situation? How many Newton's laws do we need? 2. If we had a massive string, we would have to write an additional law for the string. That would make calculations much harder, because when objects move, the length of the string also changes on both sides, which means we have to deal with variable masses. We need to integral things. If it's massless, everything is doable in 5 minutes or less. So please just take a minute and draw a free body diagram for each weight first. Choose the axis and draw 2 Newton's laws. Okay? And I will do the same soon. Clearly, the magenta box represents the heavy one. The green represents the light one. We release them from rest, so we know how they should be moving. Theoretically, I could complicate things. I could kick it or pull it first, but why would we complicate things if we can keep them easy? So the heavy one will be traveling downward. Now, when we say down, this word, traveling down, what does it describe? What physical quantity does it describe related to a motion of an object? Yes? The velocity or displacement. Does it describe acceleration? No. In addition, we need to say something about how velocity changes. Yeah? And how velocity changes? It increases, the object traveling faster and faster, speeding up. So for that guy, the acceleration also should point down. All right? So how many forces should we show acting for each box or block of weight? How many? 2. Theoretically, again, theoretically, air friction might mess it up. We ignore that. So there's only force of gravity and force of tension. Here we have another force of gravity and another force of tension. Again, from the most general point of view, those are different forces. They applied to different objects. However, because the string has no mass, we can write this condition. Now, this object travels down and speeding up. This object travels up and also is speeding up. So we can see clearly that acceleration are also different. However, because the string doesn't stretch, we can apply the same condition again. The magnitudes of those accelerations are equal. Now we got to choose the positive direction. And in this room, we always choose it up for the vertical direction or to the right for the horizontal direction. Now we have to write Newton's laws twice for each object, a law. How does the law sound? Please. How does the Newton's second law sound? Absolutely. That's one of the versions of the Newton's law. It just, since normally regular people hate fractions, we multiply everything by m, and this is how we write it, which mathematically is the same. And this technically should be 1, 1, 1. If I write the Newton's law for the first object, this is how I should write it. And now we can apply a definition of the net force. So we can continue. If we apply a definition, we're replacing this abstract symbol. I forgot to mention this symbol, which is a capital sigma in Greek, replaces word or represents the word sum. That's it. It's a standard symbol for the sum in mathematics and physics. And what does sum mean? Yes? Right? Not subtraction, not division, not multiplication, addition. So we should add, what should we add? 2 forces acting on the first object. This is the first force, this is the second force. So far this equation is generic. We use vectors. If we don't like vectors, and we don't, we should rewrite the same law using components. And in general, just a review, we have 2 components. However, in this situation, relative to the x-axis, all vectors have the same component, which is 0. So this is 0 equals 0 plus 0. Not surprising. But this equation tells us m1 times. Now, these vertical bars represent the magnitude, the word magnitude. So this symbol represents the magnitude of acceleration. It is positive automatically. But the component, y component of this acceleration relative to y-axis should be what? This acceleration points down, it points up, so the component should be negative. So this is how we write it. Clearly showing it's negative. Tension points up, gravity points down. And one more thing. Since we are given a symbol for the mass, let's just use that symbol, capital M. And now, well, much faster. Again, M2, A2 should be equal to the sum of all forces acting on 2. But relative to y-axis, well, first of all, we use lowercase m for the mass of the second green box. The acceleration points up, positive. Force of tension has the same magnitude, points up, positive. But gravity points down, has a negative component. That's the equation. So now we got to solve two equations. Now, the first step is to copy these equations on a different piece of paper. Oops. This is a situation we've met before many times. We have two equations and two unknowns. We consider that we know little and big masses, we know g. So what we don't know is acceleration and tension. Two unknowns, two equations. We got to do some algebra. There are different ways to solve these equations. So today I want to demonstrate one more, which we haven't used so far, addition. So what I want to do, I want to eliminate a variable. And what I see the same clearly is tension. So how can we eliminate a variable? And in mathematics, the word eliminate or get rid of has two possibilities, subtraction or division. So I want to use subtraction. It's easier. Well, first I want to rewrite this equation. Just multiply everything by -1. So this would be positive. That becomes negative. That becomes positive. And I keep this equation. And now I want to add these two equations, which leads to subtraction of these two variables. I'm literally adding. So this plus this supposed to be equal to this plus this plus this plus this. So what we have here is this unknown acceleration as a common factor. What we have on the right side of this equation, these variables cancel each other out. So what's left is hence, this is a general expression for the acceleration. This equation tells us immediately again that actual acceleration cannot be equal to g. First of all, if masses are equal, that's 0, acceleration is 0. But if masses are different, the acceleration depends on, well, like this. But of course, first time it has been solved backwards for g. The physicist, whose name was Atwood, that's why the device called Atwood's machine, French guy, he measured this acceleration and used masses and calculated gravity. That's it. Any questions? This is, again, just a straightforward application and slides and the equation. So here we have a numerical example. What would happen if we had masses, well, 210 and 200? The actual acceleration would be 0.25. And the acceleration due to gravity is 10. Okay. Next force. We've named many forces. Yeah. Force of gravity, force of friction, normal force. Now we're going to talk about official definitions. First of all, normal force. A normal force is a force, we said, which prevents an object from falling through a surface. But an official definition is that normal force is the force which is perpendicular to the surface. So if I push on this scale, the scale pushes back. That will be my normal force. If I place a weight on it, the weight acting on the scale, that's what we read, but the scale, Newton's third law, is acting on the weight, and that's what the normal force is, the force acting on this object. But the magnitude, of course, is the same. How can we change normal force? Well, there are different ways. We can take this scale, go to the elevator, and try to move up and down. I hope we will solve this problem today. Another situation is we can tilt the surface. This, actually, I know it's going to fall, but let's give it a try. About 1 Newton. If we start tilting it, it should change. Does it? Well, it does. Why? Well, because of the definition, normal force is not the force opposing gravity. Some people think that's the normal force is the force opposing gravity. No. By definition, the normal force is that force which is acting on this object perpendicularly to the surface. And again, this statement doesn't require understanding. It's a definition. It requires acceptance. You accept that or not. If you don't accept this, you should leave. That's it. This is the normal force. That's it. And when you change the angle, the normal force also changes. Yeah? But of course, this is the easiest situation. Now, several slides later, we're going to talk about friction. So I just want to point at this definition and forget for several minutes. As we said, when an object is on a surface, the contact happening here, in general, the force acting from this surface on this block might have any possible direction. So if we measure or calculate components of this force, this component we just said has a name normal force, but this component parallel to the surface has a name friction. That is an official definition. How can we calculate friction? Several slides later, it's just two definitions. So just remember, if you read by any chance this name contact force, that's what it means. The actual force due to a contact between a surface and an object. It always has two components, normal and friction. And according to the Pythagorean theorem, that's how they're related. That's it. Now, let's do a simple calculation. Here we have force of gravity acting down, because force of gravity always acting down, and it should be equal to about 400 newtons. The force which is perpendicular to the surface and supporting the object has a name, normal force. To calculate the normal force, we have to apply the Newton's second law. And the Newton's second law says m times 0 should be equal to normal force minus 400. 0. So normal force, 400 newtons. This is an illustration of this statement. Normal force is always wherever it is. As long as we apply Newton's law correctly, wherever it is, that's a normal force. That's it. My second question for today to you. I am changing the situation. This is the value of the normal force when nothing is touching else. Nothing else is touching this way. But what can I do? I can push, or I can lift. These situations should change the normal force. So the question is how? You just need to calculate the normal force for both cases and choose one. So you can use the free body diagrams given to you. This letter W is another standard representation for force of gravity, which also people sometimes call weight. Sometimes this term might be confusing. We'll talk about it later. So what's going on here? Well, we just have to apply two diagrams, right? At the top, the Newton's law says mass times acceleration, and it's 0, should be equal to normal force, which points up. Strictly speaking, I should draw the axis, but in my mind, it's always up, right? Now, minus 11 newtons because of the hand, minus 15 newtons because of the weight or force of gravity. Normal force equals 26 newtons. Here, mass times acceleration is equal to. Now, we push up with 11 newtons. Normal force directed up, but force of gravity still points down. So, fifth, bless you, 4. This is a prerequisite for this question. Well, this is how we solve it. Now, what do you think? What do you think? So I'm not asking you for the actual value. I'm just asking you how would it change? We have calculated that when this object was just resting, normal force was equal to 400 newtons. Now what do? Now we're just pushing it. Imagine like you pushing the cart, shopping cart. So this is additional force of 10 newtons. Would it change the normal force? If it would, how? And this situation is directly related to this situation, right? So we may be pushing from above or pulling upward, and that changes the normal force. So in this situation, we should expect the change, so don't choose answer number 1, right? Well, what did you choose? Exactly. Well, again, all we need to do is just draw a diagram. Now, I want to show you a kind of technical element which helps to deal with forces which are not horizontal or vertical. This vector, 10 newtons. As we perfectly know now, every vector has components. And by a definition, components are vectors which, if we add them up, equal to the original vector. So we have 2 components here. Let's call it f. The horizontal component fx and the vertical component fy. If we look at this picture, the free body diagram, well, the actual free body diagram looks like this: gravity, normal, and the applied force F. But in mathematics, we know that if something is equal to another thing, if we replace the first thing with another thing, it doesn't change a thing. That's the thing. So we can replace this vector with its components, literally. This is not the actual free body diagram, but we call it equivalent. And of course, the x component doesn't affect the normal force. Only the y component affects the normal force. And the y component points down. So this is exactly this situation. That is why normal force increases. And we can calculate now the actual value. Because, well, we don't know if the box is at rest. We don't know if it's moving. But it doesn't matter. Because even if it would have been moving, the motion would have been horizontal. That wouldn't affect forces in the vertical direction. So relative to the y-axis, we still should write m times 0. This could have been vertical component of acceleration. It should be equal to what? Normal force, which is positive, minus y component of the applied force, minus mg. Mathematically, that would be normal force minus. Now we got to use geometry. This is our triangle, 30 degrees, Fy, the magnitude of which should be equal to hypotenuse times sine of 30. And we can solve it for the normal force is equal to mg plus that additional component. or in numbers, 40 times 10 plus 10 times sine 30. Sine 30. 1/2, so 4 or 5. This problem doesn't require any new knowledge. No, we've used all previous knowledge, including some geometry. What will change now? Now we know the normal force now actually should be less, should decrease. So immediately we can introduce components. That's supposed to be the new normal force, still force of gravity. That's the positive y direction. The equation now, m times ay equals normal minus magnitude of this component minus mg. This is 0, hence, oh, sorry, plus. Now it's plus. Positive direction, positive direction. So now the normal force will be equal to mg minus this component. So now it's going to be 400 minus 5, magnitude same. So 395 newtons. Let's do this situation. We saw in experiment normal force changes. Well, first of all, the force of gravity, no matter what, still points down, still is equal to 400 newtons. I'm sorry, I have to add the angle. This angle is still 30. We use the same angles everywhere again and again and again. Now, please copy this picture and draw the normal force. Well, in general, when we draw a vector, just randomly drawing vectors, we can have a variety of choices. Now, what do you think about this vector? Would it be a correct choice for the normal force? What do you think? No? Yeah? Which would be correct? The one which is perpendicular to the surface. Why? Why it has to be perpendicular to the surface? Because that's the definition. That's the only reason. Because everybody else agreed to call this vector, which is perpendicular, normal force. We may have other forces like friction or something else. Why not? It could be resting. It could be sliding. It depends on other variables. Here, no. All right, should work. Rest, 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 slides. So this picture doesn't tell us if it's resting or sliding, but we shouldn't care, because all we need to do is to relate normal force with the what? Well, there's only one force which has another component perpendicular to the surface. This is a case when we don't usually choose x and y axis like we used to horizontally and vertically. This is a case when we choose axis differently. There is a rule of thumb, not the law, but to make our calculations easier, we should choose at least one axis in the direction of the motion or possible motion. So if it would be sliding, it would be sliding like this. So this is the direction, natural direction for the well, usually it's called x-axis. And that will be the natural direction for the y-axis. So in this situation, friction or whatever else might be parallel to surface doesn't have y components at all. We have only two forces which have y components. Normal and where else? What other force is? Yeah. mg, yeah. mg has two components, x and y. So this arrow represents the x component of force of gravity, F mg. This arrow represents the y component of the force of gravity. And if we write the Newton's law relative to the y-axis, it should be m times ay equals normal, well, minus magnitude of mgy. Because normal points in the positive y direction of our choice, and mg points in the opposite. And even if we had acceleration, this component would be equal to 0 because of our convenient choice. But if it would have been at rest, the acceleration would be 0 anyway. So this is 0, normal minus mgy. And turns out, in this particular situation, that's how we should calculate the normal force. Well, the last question is, how do we calculate this component? We need a triangle. This is a right angle triangle. In this triangle, mg is the hypotenuse. All we need is an angle. And that geometry has nothing to do to physics. So geometry. If I extend this, that's supposed to be 90. This is 30. Large triangle like this, 30, that's supposed to be 60. 90 degrees, that's supposed to be 30. Or we could call it theta for now. So normal force supposed to be equal to mg, which is the hypotenuse times certain function of this angle. If you see what function, sine, cosine, or tangent, should we use, you're all set. Otherwise, you should refresh your equation sheet, how we use right triangles. So what should I write here? What function? What do you think? Say something.
Where?
Which function? Sine, cosine, tangent for this angle? This is a triangle. This is a triangle, hypotenuse, angle. That's the side we're looking for. Couldn't hear you. Possible option. What do you think? Possible option. What do you think? All right. We have different situations. If you think sine, please raise your right hand. Well, you have to raise. You said it. If you think cosine, please raise your hand. Well, I'm with everybody. That's how it's supposed to be, right? But not in physics. In physics, sometimes majority is wrong. Well, in politics too, as we know now very well. Now, that's it. That's the equation. We can plug in numbers. So mg cosine 30, wherever it is the number. Yes? You have a question? You have an answer? Please tell me. 346? 346. If it's wrong, that's her fault. You have a question? Any questions? All we have done is applied a straightforward definition of normal force and geometry and Newton's law. So again, the same slide with one more equation. In this situation, normal force is equal to mg, but in other situations it's not. And if you choose all angles and axes, like in my example, that will be your equation. If you choose different angles or axes, your equation will be different. Neglect friction and calculate the acceleration of this box. So friction could prevent it from sliding. With no friction, it will slide. So what do? Normal force of gravity, and that's it. No more forces. The normal force, as we said, equals mg times cosine theta, 30 degrees. Does normal force affect the motion? No, which is a good thing. So again, we can choose the same two axes, x and y. That's velocity. It is speeding up. That's acceleration. All we need to do now is to write the Newton's law relative to x-axis. M times ax is equal to. Well, technically, we should write F and x. But since normal force is perpendicular to x-axis, that's 0. Plus, now we need to use this component, mgx. And it's positive, so plus mgx. Again, m, a, because acceleration is just equals this component, equals mgx. First of all, interesting fact, we can cancel masses. So just gx. And of course now, in the same triangle, we just have to use the opposite function. Not cosine, sine. So this angle is, this angle will be 30, because that angle was 60. So equals g times sine 30, which is about 10 times a half, 5 meters per second squared. Just another application of the Newton's law. Any questions? Combined with some geometry. The most probably important part of this strategy is seeing that you should use the flexibility given to you. In this situation, the flexibility is in choosing the direction of your x and y axis. Yes?
Could you just go over how you got the angles?
That's a good question. So basically, the best way is just redraw the whole thing without any additional elements. As additional elements, they come from physics and they don't matter. What we have is this, theta. And here we also have a point with other vectors. One points this way, one points this way, and this vector, let's call it, please call this vector, name it, give a letter. Capital or lowercase? Capital A. So this vector has components ax, ay. This is equal to ax again. So no matter what, a is equal to square root of ax squared plus ay squared, if we need it, but Pythagorean theorem. But now we need to relate these angles with this theta angle. Again, there are multiple ways to do that, multiple. What I like doing, just extend the force of gravity, well, extend this vector, because now I have another triangle, 90 degrees. And now in this triangle, let's call it B, C, D. BDC is theta. Angle CBD is 90. So angle BCD is equal to what? What? 90 minus that theta. But now we go to this triangle. That's what we're looking for. This angle should be equal to this 90 minus BCD. So it's 90 minus theta. I find this reasoning kind of beautiful. And if you don't find it beautiful, something is wrong with you. That was a joke. Did I answer your question? So now when we have talked extensively about normal force, we can introduce a new definition. Usually people call this weight, but that's wrong. We should call it technically the apparent or apparent weight. And by definition, the apparent weight is what the scale measures. That the force acting from a scale on the object put on the scale. That's it. And according to this definition, the apparent weight always is equal to the magnitude of normal force. That's it. That's what we need to remember. So when people say calculate weight, they mean normally calculate the apparent weight, and that means we just need to calculate the magnitude of the normal force. Why would it change? Well, we know why. We can push, we can lift, we can angle. That would change it. Or, again, we can walk to the elevator, and in the elevator, if it starts moving, the reading changes. So that tells us that every time we just need to calculate this new thing, apparent weight or shortly weight, we just need to calculate the magnitude of the normal force. And as we know, the normal force is wherever it is, wherever Newton's second law tells us. So what situations may we have with an object in elevator? Well, the velocity might be pointing up or down or be zero. Does it help us? Not really. Because apparent weight related to a force. Force is related to Newton's law related to acceleration. So we have to relate this motion with acceleration. What options do we have? Well, speeding up, acceleration also points up. Slowing down, how does acceleration point? Opposite to velocity, which means here, down. Now, if the elevator moves down, the word moves describes motion, velocity. But what if it's speeding up? How does acceleration point? If it moves down and speeding up, the acceleration points down. But if it moves down and slowing down, the acceleration points up. That's what we need to remember. It's not about velocity, it is about acceleration. Now, if velocity is 0, if it's long time 0, it's just at rest, acceleration is 0, or velocity is constant, the elevator is moving, but velocity doesn't change. What does it say about acceleration? Velocity is constant, acceleration is 0. That's it. That exhausts all possible situations. And for all those situations, there's only one law we need to write. Newton's second law. So for this guy in the elevator, we have normal force and force of gravity. Does the cable touch the guy? Does the cable touch the guy? That would be very, very bad for this guy if the cable would attach to the guy, right? That's why the cable is not attached to the guy. Remember that. The cable is attached to the cabin, and cabin moves the guy by pushing on his feet. But the acceleration, let's point it up, in general, might be directed up, might be equal to 0, or actually might be directed down. How can we describe all situations in one? Simply using the general symbol for the y component of the acceleration. In this situation, y component is positive, so y component is equal to magnitude of it. In this situation, y component is negative, so y component is equal to -1 times magnitude. Y component is negative, y component is positive, equals minus y component is 0, y component is 0. We just need to use this symbol in our equation. In our equation, mass of the guy, not the mass of the elevator, we are writing an equation for the guy, should be equal to m times y component of acceleration, and that should be equal to normal force minus gravity. Hence, if we want to calculate the normal force, which equals to the magnitude of that what we call apparent weight, that will be equal to mg plus m times the y component of the acceleration. That solves all possible problems all at once. If acceleration is 0, the apparent weight is equal to actual simple weight mg. If acceleration points up, we should add a positive number. If acceleration points down, we should subtract a positive number that decreases. Any questions? Yes? This?
It's where you put in apparent weight.
This?
Yeah, like that.
Or this part? Which part? Left or right?
Both of them. Like from there to the end.
This comes from a definition of apparent weight. The apparent weight is that reading on the scale, and according to Newton's third law, it equals to the magnitude of normal force acting from the scale. This comes from the Newton's law. This literally comes from this. I just solved this for the normal force. All right, so I had some extra slides if I didn't have to use them. Now here, an example of a situation where we use this backwards. This is that's what we call an actual weight, mg. For this guy, mg, 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 mg is 700 newtons. But he is on a scale in the elevator. Probably a physicist or crazy. And every time he reads different numbers, and depending on those numbers, and those numbers are equal to the magnitude of the normal force, and at the same time to the magnitude of the apparent weight. So we can extract the information about acceleration in every time. And what do we do? Well, we just have to write an equation, again, the same equation, positive y-axis. Single diagram, W, which is mg, normal force, which is equal to the magnitude of this, what we read, apparent weight, and acceleration, which in general might point in any direction. So m times ay should be equal to this minus this. So ay should be equal to this minus this over m. What do we have here? Ay should be equal to 700 minus 700 divided by m, 0. So maybe the guy is at rest, maybe he is moving, but if he moves, the velocity is constant. Here, ay equals 1000 minus 700 divided by, well, do you know the mass of the guy? Well, technically not. We know his weight, but how can we calculate the mass? Yep. Positive. So the acceleration actually should point up. Here, next part. Negative. So acceleration points down. If acceleration points down, does it mean he moves down? No. Because velocity, direction of velocity depends on how he moves. And finally here, what does it mean? It means he's just falling down. So it means he has enemies. They cut the cable and he's just falling down, freely falling down. That's why this situation has a name, free fall. That's why the acceleration due to gravity also has a name, free fall acceleration. Every time when you're falling freely, you experience that acceleration. If you're falling freely a short distance, that's fine. If the distance is long, like 5 stories, that's bad. Any questions? Moving on. I want to ask you this question, please. What do you think? There is a statement, and you should choose agree or disagree. Do you agree with this statement? If net force equals 0, the object is definitely at rest. And this I want to check. This question 4, this question I want to check. So 1 for yes, you agree that when net force is 0, the object is definitely at rest. No, you disagree. So now we go to here. Now we go to summary. Now we go to question 4. Very good. I'm glad. I've seen different distributions, but now the no is the correct answer. If net force equals 0, that only means acceleration equals 0. But if acceleration equals 0, it doesn't mean velocity is 0. It means velocity just constant. So very important point. And let's just reason through several, not quantitative, qualitative situations. What is happening? Well, in outer space, a ball is flying, and here an alien kicks it. You know aliens exist, right? Just go to the movie. Kicks, what does it mean? It's a force which has been acting over a very short time. That's it. If the force was acting, hence acceleration is not 0. So velocity has to change. How? Well, velocity is equal to initial velocity plus acceleration times time. The time is a fraction of a second, but still, that was the original velocity. How does acceleration point? That's instantaneous velocity. The acceleration always points as the net force points. So, plus acceleration times time equals, so we need to add 2 vectors. The new velocity points like this. But after the kick, that's why we call it a kick. Does force act on the ball? No, not anymore. So after the kick, velocity remains constant. That's how it's going to travel. This is the physics, not equations. Now, a burst. What is the difference between a burst and a kick? What do you think? What do you think? There is no difference. A burst also represents a very short action. So there will be no difference here again. What is the difference between a burst and a thrust? Yes. Continuous action. So in this situation, force is acting over a long period of time. So velocity will be constantly changing. At first it will be changing to this direction, but then it should be changing to this direction, but then it should be changing to this direction. So the object actually should be traveling like this. Have we seen something like that before? Of course. We just saw it differently. Take this picture and flip it. That's exactly what's happening with the ball under influence of force of gravity. When it rolls on a table, net force is 0. Gravity and normal cancel each out, but as long as it lifts the table, force of gravity starts acting on it continuously. So velocity starts changing continuously, and that's what we see. So the difference between a short action, which is important when we talk about collisions in the future, and the continuous action. A short action changes the velocity immediately, but after that, velocity remains constant. A continuous action changes velocity continuously. Any questions? I've promised you some time for your questions, but I will answer the questions only if you have them, because if you don't have any questions, I'm just going to move on to the next slide. Any questions about anything? Yes?
At the first homework, there was a problem that you had to find the acceleration by using two different sections from a triangle, but then at the solution, it didn't take the entire time when you divided for the different velocities. It divided the time by two, and I was confused by that.
I'm not sure what problem you're referring to. Anybody can help? What is happening there? Yes? With the graph? Is that problem with the graph? Because I remember the problem with the graph. There is a graph velocity of the function of time, right? I cannot hear you.
Yeah, that's the one.
So it looks like this. The race runner runs and you needed to calculate acceleration.
Yeah.
And,
Yeah.
well, okay, quickly. First of all, I'm not sure if you have noticed the note. That was 10 seconds, I remember, right? But the actual time of the race, a little bit above that. It's not exactly 10. Now, what is happening? If we draw the axis, starts from 0, for example. So x1, well, it's not x, it's time 1 related to x1. It's x final related to time final. So it's the guy is speeding up, travels faster and faster, and then the guy travels keeping velocity constant. So acceleration is not 0. Acceleration is 0 here. This velocity, I think, was given like 7, 4. All right, let's call it 7. I don't know.
12, I think.
12. So, and this time was 4 seconds.
Yeah.
For acceleration, you don't need to know anything else. Yeah, the initial velocity is 0, final velocity is 12. This time is 4. Acceleration delta v over delta t, 12 minus 0 over 4, 3 meters per second squared. The real question is how to calculate this, I suppose. Now, to calculate this, I know what you're saying now. Okay. They used a slightly different approach. So first of all, in this situation, delta x is equal to distance traveled. Yeah, no difference. As we know, distance traveled is equal to average speed times time. Because average speed is distance over time. So this is the average speed times 4. So if only we knew the average speed, because it changes. Now there's a fact which we could prove algebraically relatively easily, that for the motion with constant acceleration, average, well, technically average velocity, but in this situation also average speed is equal to mathematical average, initial plus final over 2. That's where 1/2 came from, because it's going to be 0 plus 12 over 2. But If you don't know this fact, you could have used our general approach, motion equation, velocity equation, and stuff, you know, and get it done. This is kind of like a shortcut. And I think, yeah. Well, okay, it will take maybe 5 to 7 minutes to prove it. So if you want, we can do it on office hours. Yes?
Are office hours like Monday office hours?
Yes.
Friday?
Yeah, today is Monday. Outside of this building, it's Friday, but inside, it's Monday. Please, questions? Yes?
What is the setup of the test like? I believe you said it was 8 questions.
7 or 8. I honestly haven't decided yet. I still have time for that. Begins at 8, ends at 9:50 on a time. And the equation sheet will be printed out and provided. You may bring a ruler or something if you want to draw straight lines. Of course, a calculator, eraser, ID just in case, which you also can use as a ruler. Yes? Cannot hear you.
Can we use graphic calculator?
Yes, no problem, but not a phone. Any questions, please? All right, yeah.
Will there be elevator problems?
I don't know yet. You see, everything which has been covered before this might be on exam, but we have covered much more topics than problems. So theoretically, you could expect a problem related to any topic, but practically only certain topics will be presented in the form of a problem. That's what we have learned. That's the exam. And topics, again, might come from all sources: lectures, labs, and homework. All right, no questions? Thank you. Yeah. Well, you can go. We can just talk personally now. And I'm going to go to office hours. I'll be there in like 10 minutes. Yes.
I still want to know about the masses and mass string.
If you have massive string, you need to write 2 more Newton's law, one for the left part of the string, one for the right part of the string, and that changes things, especially because when length changes, mass changes, so it's going to be much more complicated problem.
I'm wondering if it would be that
Well, if it would be real, well, if mass becomes large enough, that will be significant. If mass is not large enough, it's insignificant. And when it's insignificant, we just set it to 0. We neglect it. Yes? There is a, yeah, well, we cannot, but you could try just using thin string and heavy chain and see the difference.
That's true. Okay. Thank you very much.
Sure.